Okay, here we go with kind of an experimental thing where I'm going to record a lecture video for you and expect you guys to watch it on your own um, while the other crew and I are in the classroom having an exam. So let's see how this goes, and if you guys particularly like it, let me know about that, and we can talk about doing this for future ones. If you particularly hate it, also let me know that, so that maybe it counterweights if somebody does like this. You might add your voice to saying that you don't like it. Okay, and let's start out with kind of a review of our lab 2, which I'm going to tell you about it in a couple of slides from now, but I want you to turn in a version of this this week, and then we're going to talk about maybe revising it as we go. So in part A of the lab, this was intended to get you used to working with balances and glassware and volumes and different glasswares and stuff like that. So that was a part of the intent of the lab. And then it was also to demonstrate accuracy. Now, that's separate from precision. We'll get to that. But that some glassware is more accurate, meaning more on target with what volume it purports to measure than other glassware. So looking at that, which kind of glassware did you find most accurate when you did this? And as a note, any of you who I think we have a chemistry major and several sustainability majors, you guys will have to do Quant, which is Chem 3311. You will get much more practice on measuring precision of this glassware, which is the plus or minus how much. Here we're really talking about the accuracy. If it says it's measuring 60 mils in that beaker, is it really measuring 60 mils? If it says it's measuring 10 mils in that pipette, is it measuring 10 mils, and which ones are more accurate? Precision comes later. Another note, it is important for you to report the results that you got, not necessarily, well, definitely not the results that I expected you to get. So I know which of these glasswares I expect to be more accurate, but that doesn't matter. I want to see your data collection, and the conclusions that you came to. Okay, now in part B of the lab, the idea was that you would make a graph of sugar concentrations. So my graph here has sugar concentrations in percentages on the x-axis, and then versus the density that we would measure, and that's on the y-axis. Now, I don't think the lab specified which axis was which, and so you have freedom to decide there. I chose density as the y-axis because I kind of think of it as the dependent variable here, that the percentage is causing the density, and we tend to put the dependent variable on the y-axis and the independent variable on the x-axis. But you could actually do this graph either way and it'll still work. Okay, so then you made up these different percentages. Now I have stuck, by the way, a column in between, and this is a thing to think about in future labs, is you don't have to turn in exactly the way the thing is set up. I didn't like the way this data table is set up. I thought that it would make more sense to have this extra column in here where I used that density table that we printed out a whole page of, and so I converted my milliliters of water into grams of water here, and then I could take my grams of sugar divided by my grams of water and get a percent sugar content. Okay, and then this column, this last column, that's going to be measured, and we measured that by taking a known quantity, 10.00 milliliters, using that pipette, and measuring the mass of that. Well, once you get the mass, then you can divide by the 10.00 mils and get a density in grams per milliliter. That's what goes in this last column. And then I am plotting this percentage, 4.26%. Let me change to a pen here so I can mark on it. So it's really not straight. 4.26%. Density 1.10. Yeah, right in there. 1.1070 grams per mil. And then plotted each of them this way. Now I did this in Excel. And if you look in, now you can certainly do this by hand, but also, I mean, I am a big fan of using the technology when I can. I put my spreadsheet into the lab folder under content on Georgia View, and you're welcome to use my Excel sheet if that helps you. If it's easier for you to plot it by hand and show it that way, that's perfectly fine as well. Okay, so what we're doing here is we're making a model, okay? And model making is a big part of science now, where we create, in this case, a mathematical model to use to predict something, all right? And in part C, we're going to use it to predict an outcome, okay, using that model. So I do understand that some of you only have a couple of data points. Some of you have more, and more is better. But plot what you have, and let's look at what happens when you have more data or less data. All right, finally, in part C of the lab, we want to take this data model, this mathematical model that we've created here, the graph, and we want to use it to predict that outcome. So the prediction part is taking an unknown, that sample solution of, I don't know, somebody said all the fruits. So you take that and you use it to predict an outcome. So let's say, and I'm making this up as I go here, let's say we got about 1.072 grams per mil, right? So if we have 1.072 grams per mil, we would carry that over to the graph right here. So that's where it intersects my trend line. And then how would I then predict a percent solution for that? So look at this. So you know that here that this 15-ish percent had a density here, and it sloped up until you got to this 19-ish percent here. Well, you'd expect it to be right there in between, and you can just drop down straight down from that and get a predicted concentration, and then estimate. Well, let's see, what would that be? I would guess about 16-ish percent. My graph is set up in fives, and that's terrible. I should probably have done it in ones so that it would be easier to graph. Now, if you are very proficient with maths, you might see a way to use that equation to back calculate your x value in this case, which would be even better. Just show your maths if you do that. Show what you did. So it is, of course, what we would do in the upper level courses, but you're not really required to do it here. You can just do it graphically. Just show that what you drew out. If you do that, you can just draw it on there. You don't have to animate it, of course. All right, so that gets to what do I want you to turn in. So I want you to turn in a little short narrative of what you did, and later on, if you're writing more complex scientific papers, we would call that a materials and methods section. Doesn't have to be that formal. Just kind of write up what you and your partner did on the different days. I know they'll be a little slightly different. And then do show the data that you got. Arrange it in tables, however you think it makes the most sense to present your data. Present your real data. You will notice that that my data shows up here as a perfect r square equal to 1, and it should never be that perfect, of course. That's because this is made up data, and so it fits it perfectly. Yours won't be that good at r squared if you do an r square, but you'll have some noise. You might have some here. Let me plot some here. You might have some that plot here, 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 and you would still draw your trend line in between that, and so you'll still get a line. Don't connect the dots. You have to kind of shoot the middle, one straight line. Straight line is actually redundant because lines are straight, not curved. So that you kind of incorporate a best guess or a best fit line, it's called, for all the data. Okay, and then also put in your lab what your predicted percent sugar solution is, and we can talk about all the different results as we go. Turn that in. I'll make an assignment for it. I haven't done that yet, and I'll do so. Let's say turn it in by, some of you guys have an exam on Thursday morning, so let's do it by Friday evening. And then what I intend to do with that is we'll have another one turned in next week that's kind of, I want to look at what y'all turn in this week and talk to you about how I could possibly grade that. Also feel fairly at ease because I'm going to go super easy on grading this first time through. All right, so from that lab stuff, I'm going to ease right over into the lecture part because they kind of go together here, and that's on purpose. So we just did a percent concentration, right? You figured out percent sugar concentration. Now technically, the way I set my table up was mass over mass, and so you can use this M over M notation with percentage. There are other kinds of percent composition. You can do volume over volume, which assumes that you've got like a liquid put in a liquid. You can do that with a gas over a gas. That would be fine as well. And then you can mix your, I don't like this as much, but I see it a lot, mass over volume. So percent mass over volume would just take the grams of sugar and divide by the milliliters of water. And you can see that that's fairly close because a milliliter is about a gram, but I don't like mixing the units like that because they don't actually cancel out. And I kind of love my dimensional analysis, so I don't like this, but I want you to know it exists. Okay, so using a percent composition like this, these things are pretty easy to calculate. Unfortunately, they don't really work very well in chemistry, and we rarely use percent composition except for very concentrated solutions. Because the percentages, well, for one thing, the percentages that we're using are going to be very small. And for another, there's confusion with the type of the way you calculated above, mass over mass, volume over volume, or mass over volume. And there's some other problems with it too. So it's there, but it's rarely used for actual detailed chemistry stuff. Okay, much, much, much more common is for us to use molarity. Now, chemistry is famous for its molarity. We're going to use this all the time. So of all the concentration units, I care more about molarity than any of the others that I'm going to tell you about, including percent composition. Molarity you are going to see over and over again. If you take two chemistries, you're going to see it all through both of those chemistries. If you take more than two chemistries, you're going to see it in every one of them. I'm trying to think. It's hard to guess whether or not you would see it in one particular course called Physical Chemistry 2, which is all about quantum. Other than that, you will see it in absolutely every chemistry course. It's so incredibly important to the way we do chemistry. All right, so molarity is symbolized by a capital M. And remember, my triple equal means is defined as. So molarity is defined as moles per liter. Liter's -1, so it's in the bottom. So let me just rewrite that to make sure. Molarity equals moles over liters. Okay, and it's moles per liter of total solution, not necessarily solvent. We'll get to that in a second. But it's, so once you've made up the thing, well, my total solution volume is 500 milliliters, so 0.5 liters. Cool. And I've got 2 moles in there, right? 2 moles in 0.5 liters. So 2 divided by 0.5 would give me 4. So that would be a 4 molar solution. Okay. It's by far the most common. And okay, so I wanted to define some terms here. So I'm going to use these probably without thinking about them, but a solute. Solute is the thing being dissolved. Solvent is the material doing the dissolving. So it's usually water or an organic solvent. So we used water in the lab. Sugar was our solute and water was our solvent. And then solution is put together. So sugar solute, water solvent, and sugar water solution. So the solution is actually after it's dissolved and you've made up the solution. And unfortunately, there are confusing bits that go with this. So molarity was moles per liter, and molality, which is a little m, is moles per kilogram, and technically it's even more confusing because it's kilogram of solvent, not of solution. We're not going to use molality. It gets used some in quantitative work, but if you do your quant here at Dalton, we rarely use molality there either. I don't know who uses molality now, but just know that it exists. Sometimes it gets thrown out there on exams when we steal questions, like you've seen me do before, without thinking about it. Ask me if I use a molality thing, because I probably didn't mean to. It is a little bit in Chapter 11, so you might see it in Gen Chem 2. So that this way you can look back at your notes from this one and see what molality was if you encounter it later on. Let's see. Now, there's not much numerical difference when you're looking at dilute solutions, but when you're looking at concentrated solutions, the numbers can be significantly different. Another concentration type is normality, and I couldn't find this one in your textbook at all. Let me know, somebody, if you do find it. It's capital N, and so it's a little more confusing. This is usually used with acids and sometimes with charged species like ionic solutions and stuff like that. So it's moles of charge equivalents per liter. So the simple way to look at this is if you've got a doubled charge, you just double your molarity. So it's just like calculating molarity, but then you're just adjusting for the charge. So like a 1 molar calcium 2 plus solution, 1 molar would be 2 normal because you're just multiplying by the charge equivalence. Like I said, I usually see this used with acids. You're not going to encounter this any further in Gen Chem 1. You'll sometimes see these in, like, especially I've usually seen it in an environmental context. Maybe it's engineering in general, but certainly in environmental engineering, you see this a lot. So sustainability majors, I suspect you're going to run into this a lot in your career. ppb and ppm, which stand for parts per billion and parts per million. So it's a lot like percent, except that we're dealing with solution, not solvent. So what it means, 1 ppm is 1 part per million, right? Or like 1 times 10 to the negative 6 grams of solute per gram of solution. So like 1 gram solute, or 1 gram of solute per million grams of solution. And I went ahead and mixed these here, not on purpose, I just did it, because usually this is not really corrected for mass and you're talking about milliliters instead of grams. So 1 microgram per milliliter is the same thing as a ppm. Now, a ppb, parts per billion, is just going billions instead, so 1 billionth of a gram per gram, or 1 gram per billion grams. Microgram per liter, or a nanogram per milliliter. Okay, and technically there's all right, so PPT. PPT I didn't put on here because it can be confusing. You could use PPT to mean parts per thousand. I would not have said that. More commonly, I would have said that PPT means parts per trillion, so it just goes to the next level down, nanograms per liter or picograms per milliliter. So the trillion versus thousand is why I wouldn't use it, but technically, I think I would use, instead of parts per trillion, I would use a per mil, like percent. So anyway, just know that there's some confusing things out there. PPB and PPB PPM are the ones that you might actually run into. All right, so let's talk about calculating percentages, and we're going to step back to the ionic solids side for right now, or ionic compounds at least. All right, so let's ask what percent by mass of sodium chloride is the sodium part, right? All right, so how would we do that? Well, we need to know its total mass, right? So I'm going to look on the, so let's just consider 1 mole of it, and then we can use the stuff straight from the table. So for 1 mole, I've got 22.990 grams of sodium. And then I've also got, let's see, I've got this, so it's 1 sodium and it's 1 chloride. So I've got that plus 35.453 grams of chloride. So I get a total of 58 point, what did I get? 58.443. Is that enough? Yeah. 443 grams total, right? But now I want to know just about the sodium part, right? So sodium was this mass here, right? So to find a percentage, I'm going to take that 22.990 grams divided by my total mass, 58.443 grams. And I'm going to get 0.339. Oh, 39. 3375. All right, now I got to turn it into a percent. I'm going to go ahead and do my sig figs at the same time. How many do I have? So I've got 1, 2, 3, 4, 5, and I've got 5. So I can have 5. 1, 3, 4, 5. So I got to stop here. So 39.338% sodium. All right. So that's how I'm going to calculate the percent of a compound. So for molecular compounds, this is going to work the same way. Now in this case, let's see, I'm asking what percent by mass of propane is carbon? Now I guess you do need to know, and y'all don't have any way yet. So propane is C3H8. All right, so we're going to use that just like we did the sodium and the chloride in the previous slide in order to calculate this. So let's see. Total mass, I've got 3 times the carbon mass, 12.011. All right, and now I'm going to add that hydrogen mass, which is 8 times 1.00794 grams. And I'm going to get a total mass here of 44.0965. 0965. All right. Well, let's see. I need grams in Now, what do I have? I want to know about the carbon part, right? So that's this. All right, so that's 36.033. Divided by total mass, 44.0965. And you're going to get, so let's see, that divided by that, I get 0.817139. Let's see, I had 5 sigs there, more than 5 there. And remember that remember that the coefficients are exactly 3 carbons. So you don't have to include that in your sig fig stuff. So I just need those masses. That was 5, and that was more than 5, so I get to keep 5. Let's see, actually, did I do that right? So, yeah. So really, I can't be sure after that. But that's still 5. Okay, 1, 2, 3, 4, 5. So I got to stop right there. 81.714%. And I want to mention too that on the homeworks, a lot of y'all are getting beat up on points on the sig figs. Sig figs do not go away, so you should always consider them in every chemistry calculation. All right, so you see how we get this 81.714%. And I'll point out that, look at this, we've got 11 atoms in this molecule. Only 3 of them are carbon, but the carbon is 81.7% of the mass because carbon is so much heavier than hydrogen. So make it make sense in your head too. Okay, now for going backwards. Now prepare yourself because this one's going to be a little crunchier. It's going to take a little bit of doing, and you may have to rewatch this piece multiple times to get there, and I can do other practice ones if you want. So what really happens in chemistry is we'll do an analysis and we'll get a mass breakdown. Let's say that we have a sample, and it comes out as 83.236% carbon and 16.764% hydrogen. Now you could do some other mass if you want to, but there's no reason to make it more difficult than it already is. Let's consider a 100-gram sample. And for a 100-gram sample, we can just turn each of these percentages into grams because 16.764% times 100 grams is 16.764 grams. Okay, so that's the first trick. So I'm turning my percentages into grams by considering a 100-gram sample. Okay. Now, the coefficients in a molecule are not based on mass, they're based on moles. So we need to see, in each of these cases, how many moles of these things there are. So to do that, I'm going to need, from the table, let's say we've got 83.236 grams of carbon. How many moles of carbon is that? So I need, from the table, 1 mole. Look on the table and get from carbon is 12.011 grams. Now, again, and you've seen me do this many times, my grams on bottom here because I wanted to cancel, right? All right, so crunch those numbers, and I get, what did I get? I got 6.92998. All right, we're going to come back to this in a minute. Let's go ahead and do the hydrogen part, and we'll come back. All right, so hydrogen, I've got 16 0.764 grams times, from the table again, 1 mole per 1.00794 grams, and I get, what do I get, 16.6319. Okay, those are moles. Should put moles over here too. So those are moles in a 100 gram sample. All right, but now we really care about the ratios, right? So here's the second big trick. You find the smaller amount of moles. In this case, it is going to be moles of carbon, and you divide everything by that number. What you're doing, this is called normalizing. You're normalizing to that smaller number. Now, automatically, your smaller one is going to become a 1. That's what normalizing does. Okay, but then your other, and so, sometimes it's not just 2. In this case, it's just 2, but sometimes it'll be more than that. But it won't be a 1 or an even number usually. We're going to need to make it 1. So we're going to get, let me go back to blue here, 1 mole of carbon here. And we're going to get, what do we get on the other? Let's see, I got 2.4. Now, unless you are a geologist, you do not use decimals in your chemical formulas. In geology, we actually do. So in chemistry, don't do that. Don't do that. Chemists don't handle it very well. So we're going to need to change this up. So I need to multiply this by some number to get an even number. So 2.4 times something will give me an even number, and you're just going to have to do trial and error on this. You can do times 2, you get 4.8. Nope. You can do times 3 and get 7.2. Nope, that didn't work. Keep going, you'll find that times 5, right? So if you do this times 5, you get 12. So and all this is some mole accounting tricks. Well, I multiplied that one by 5. I got to be fair, and also multiply this one by 5 and get 5 moles of carbon. And lo and behold, we have snuck up on a we snuck up on an empirical formula. Here's the word I'm saying, empirical. An empirical formula of C5H12. All right, so this could be, in fact, pentane, which has 5 carbons and 12 hydrogens. So I made up the numbers based on pentane, but technically this is an empirical formula. You don't know. This could actually be C10H24, which does exist. It could be C15H36, which pretty likely exists. So all you know is the ratio here, but the simplest of those would be C5H12. This is how you determine an empirical formula, and you're going to have to crunch this math. So please run through this calculation again and make sure you can get it, because you know that you're going to see it on a homework. Okay? All right, another bit of calculation that we need to do. Now, what do we use M for? What does it mean? It means molar, right? Okay. And what do we use molar for? So this is solution concentration. And I'm going to use brackets. All right. Brackets means concentration. You'll see me actually abbreviate all the time. So this is solution concentration. All right. So let's see, how is molar defined? Let's look back at that slide, and I think it is defined as moles of solute per liters of solution. All right. So moles. All right. Moles of solute. I've got my moles of solute. I can use that. Okay, but I don't have liters here. I've got milliliters. So 56.78 milliliters. And if you can do this in your head, that's even better. 1 liter per 1,000 milliliters. Okay. So how many places moves it? 3. So 0.0567 8. Don't go to rounding off too quickly now, right? Because you don't want to lose your sigs. We've got 4 sigs in each of those. We'll keep them. All right, so now I can do my moles of solute. So 1 point, that's a terrible point. 1.234 moles divided by 0.05678. Oh, I should have put liters on the end of this because mils canceled out, leaving liters. What I can clean it up there. Divided by liters. All right. So I'm going to crunch those numbers right quick. So 1 point, it's going to be a large number. 1.234 divided by 0.05678. 21.7 molar. That's an extremely concentrated solution. 21 point, how many do I have? 4.673 moles per liter. Big capital M. 21.73 molar. All right. You know, you'll see that for your homework as well. All right. We're going to calculate a molar concentration again, but I mean, even though this problem looks like the previous one, this is going to get a much, much smaller value because here I do not have moles of sodium chloride. I've got grams of sodium chloride. And watch how different an answer we get out of this. So molar is still moles per liter, so I've got to turn this into moles first. All right. So I've got 1.234 grams, right? And then I've got to multiply by 1 mole per, what was that? Let's see, it was 22.990 plus 35.453. I'm going to put that in parentheses down here. Grams. All right. So 1.234 divided by 22.990 plus 35.453. So I get 0. Oops, I forgot a 0. 0.02. 1115 moles of solute sodium chloride in this case. Now we still know this 0.05678 liters from before, so now we can plug all that in. 0.021115 moles divided by 0.05678 liters. This time, I get a much more reasonable concentration of 0.3737 Alright, so instead of 20 molar, I'm looking at 0.4 molar. So make sure you can calculate that given moles or given grams. If you don't understand what I did differently, we need to talk. It has to do with converting it to the moles in the first place. Alright, now I want to talk about a very, very important, simple equation, but very important. Okay, and this says that you can rearrange and calculate any new concentration given an old concentration and volume and a new volume, or any one of the four missing variables. All you've got to do is rearrange this equation. All right, so let's see. Let's try to dissect this word problem. What are we going to do here? We're going to take a 30 milliliter aliquot. That just means to take a bit out of. So an aliquot is just a subsample. Like we're going to take 30 mils out of what was originally, so this blue solution here is originally a 1.234 molar solution. All right, so we're going to take this 30 mil subsample, just a little bit of it. We're going to take it over to another container, right? And we're going to dilute that to a new 1,000 mils total. All right, so we're going to pour that in a new one and then dilute it up to a 1,000 mark. All right, and so we want to know what the new concentration for that is. All right, so here's how this works. So do we know C1? Well, yes, here it is. So this one is going to be my C1. So I'm going to put a check mark over it. I know that. All right, here I took a volume out right here. So that was the initial volume, V1. So I know that. All right, do we know a concentration 2? Let's see. Now, what is the resulting concentration? So we don't know that. All right, I'm going to circle it. That's what we don't know. We better know that last one. Let's see. Oh, all right, so we diluted it to 1,000 mils total. So, no, see, that's a V. So this will be our final volume, or V2. All right, so good. We've got 3 of the 4 pieces we can solve for the other one. All right, so remember your maths. Your maths are not going to go away. They're going to haunt you all semester. All right, so I want to get the C2 by itself. So C1 V1 equals C2 V2. Now, if I want that V2 to go away, I need to divide by V2 so that it'll cancel. But if you do something on one side of an equation, you have to do it on the other. So that cancels. that leaves me C1 V1 over V2 equals my target C2. Okay, well now all I have to do is plug in C2. Let's plug in the pieces that we know. So let's see, C1, what was my C1? It was 1.234 molar. All right. Oh, y'all watch and see what happens with my units. They better work out, or otherwise you guys get to yell at me about this, right? Let's see. Do we have another piece? What else is on top? V1. What was V1? 30.00 mils. All right. Let's see. V2 down here. V2 goes on the bottom. 1,000 mils. Technically 1,000.0 mils. All right. Now, what will cancel? Let's see. Mils on top, mils on bottom cancels, leaving me molar, which will be a concentration unit. Yay. That's good. That's what we want it to be. All right. So now you got to crunch the numbers. So 1.234 times 30 divided by 1,000. So 0.03702 molar. All right. So do I get to keep all those? 2, 3. That should have been 4 there. Let's see, 4, 5. Yeah, I get to keep all of those. And don't be confused, because I will do this. I will use the metric prefixes of that. So that is 37.02. Watch what I do here. Millimolar, right? 37.02 times 10 to the negative third molar. 37.02 times 37.02 millimolar, or 0.03702 molar. All of those are precisely the same answer. All right, so make sure this works out. Let's see, a big trick that you'll run into. In our case here, we had milliliters and we had milliliters, so they cancel out, but I could as easily have done this as 1.000 liters, in which case you would have to convert it to milliliters first, make sure that your volumes are in the same units, or make sure that your concentrations are in the same unit when that comes to pass. Remember that you could solve for any one of these, right? You can isolate any one of those using your algebras, okay? Let me know. You're going to see this over and over again, both in lab and on exam 2. This stuff is all in chemistry. If you take any more chemistries from this, any other chemistry professor is going to come and yell at me and hit me with things if I don't teach you C1 V1 equals C2 V2. All right, and so let's see where we have. So ending up here, I have set. Well, I'm going to start with homework 6 redo. So it's now due Wednesday night at midnight. Okay, so you might want to get on that if you're going to be, well, that may hurt. You might want to do that ahead of time if you're going to take the test on Thursday. You don't want to be doing this all night right before your exam on Thursday. So go ahead with that. If this is Tuesday and you're hearing this, go ahead and get it done so that you don't hurt yourself. Homework 7. Homework 7 is going to be due midnight Saturday. So homework 6 redo, you've already done that first homework 6, and some of you need a retry on it. Homework 7 is the stuff based on this molarity and stuff in this lecture. Lab 2, okay, so that initial lab report due Friday night. And remember, don't sweat it. Work with your partner. You guys both should turn in one thing together. And then go ahead and read, it's most of Chapter 4. There are 5 sections, but most of Chapter 4, 4.1 through 4.4. For next lecture on Tuesday of next week. And finally, we're going to get to have some chemical equations and some reactions. And this week's lab and next week's same thing. We'll have some chemical reactions in them too, so that's nice. But we're finally getting into reactions, and we're going to do some stoichiometry and some yield calculations and stuff like that. So please read up and be ready to go on next Tuesday. Thank y'all. See you soon. Oh, wait, I didn't mention. Okay. So I did not put together any Socrative questions for this. So we're going to skip. There's not going to be a CW07, classwork 7, in the grade book. So later on during the semester, when you're like, wait, there's a CW6 and there's a CW8, is there one missing? It's because I didn't put one together for this lecture that's canned and all online. All right, so bye-bye.